Okay, so this is the second episode, and this one will be covering how to do grayscale conversion and using the grayscale images to predict whether the image contained is a cat or a dog. So the steps for the imports are practically the same for what we had prior. So OS, sys, CV2, random, numpy, tqdm, pickle for pickling files, keras, so a number of keras models, casual, convolution 2D, max pooling, activation, dropout, flatten, and dense. So all of this I did cover prior, so I can just move forward and do the imports. So before this, let me just restart and clear output. So we start from a clean slate. So with that now in mind, the imports have been successfully done. And just similar to what we had before, you list the folders, the number of files in the train folders, the number of files in the train and test folders, the first 10 images in the train folder, and the first 10 images in the test folder. So same process of now getting the test images and loading these data. So unlike what we had before, instead of working with the borders, now we'll be working with gray images. So what I'm doing is cvt.color, then providing the image, and then using CV2, which is OpenCV, and using color PGR, which is blue, green, red, to gray. So now that turns that into a grayscale image, and then I do a resize. In this case, we're going with a 64 by 64 pixel. Not that there is any major changes in this case. So previously what we had is 200 by 200, but something that has been shown is image classification can work with pretty small thumbnails of images. So 200 by 200 is a pretty small image in comparison to what you'd see with your human eye. But even with a 64 by 64 pixel, you can still get a huge amount of accuracy. So the advantage of having a larger one in the prior case was because it was a border scenario, so there was little information in terms of just lines. So the larger, the better, whereas a grayscale image has a lot more images. So if even a smaller image, the model can still do pretty well enough with training. So right now it's just going through the process of creating the test images and the list of these. And once it's done, you should now have your data available. So additionally, what you can do, as I'm going to demonstrate here, is you can pickle the data. So pickle dump the grayscale information, and then later on pickle read. So reread this, and that will save you the whole process of rerunning this script every time you want to retrain your model. So let's say you've closed your Jupyter notebook, and now you want to work on it on another day. Let's say next week or so on. So when you restart your model, you will have to rerun this to get back your list of NumPy array data to train your model. So in this case, it doesn't take too long, especially for the test image. It gets about 3 minutes in, so you can tell here it's been running for about 2 minutes and 48 seconds. And if you add these two, you're looking at about 3 minutes before the whole process finishes, which isn't too bad. With that timeline, you can patiently wait for it to finish. But if you assume that you have a larger data set, which is going to be the case for the second image here, for the training set, which may take about, let's say roughly 10 or so minutes to finish. So in that case, you may save some time if you just pick all your data and then using that pickle data read it later on, which takes just a few seconds and saves you the whole process of doing this again. Additionally, if you did a random shuffle and this shuffle without using seed, in this case I'm not going to provide the seed since I'm not going to pre-run this again, and that's primarily the reason you'd want the same order. And because you've already saved your data into a pickle, the data will always be in the same order. So there is little randomization that would come from really loading the data and working with a different amount of data set. So that's a big plus and something you should consider, especially when you are working with a model and reworking on it at more than one time. So if it's something that you know you'll be doing a number of times, basically it's a good idea to pick all your data. So moving on, we have the test image in this case. Now I'm just going to create a black and white image from the original image so that right now we can view it. So now we can see the number is 11,522, and from that load the image, and then using plot.show you should get right now the black and white color image. So in this case what I should have done is provided that one here. So let me just rerun this. So it says BTR to gray does not exist, and so that comes from actually not providing the full name. So that should fix that. Now we have the image. So here it looks a bit offset, more so like it's blue, but this is more of Plotly. So matplotlib basically also has its internal code of changing the color code, but the image here has already been converted into black and white. So if I wanted to, I can see how to use matplotlib to plot an image in black and white. Okay, so this should be it. And there you go, you have your black and white image. Now, moving on, we'll create our training data set, which will take a while to finish. So by my estimation, based on how long it took prior, this should take about 6 to 7 minutes to complete. So right now it's hovering over that number. And while I'm waiting for this to finish, I'll mention a couple of things that I was doing in this case. So here you have a trick of flipping the image. So by the flip, I mean, if you consider how basically you're taking a picture from a camera. So your left is your right and your right is your left. So in the same case, it's flipping an image by its middle center. So the line moving up to down, intersecting the image in the middle. So we are flipping it according to the horizontal axis. So with that, I have the previous data here, the prior image without flipping it. And after this flip, if we had an example of a dog facing left, after you flip it, you have the same dog facing right. So that creates double the amount of data that you had. So you move from 25,000 training images to 50,000 training images. And they are unique because the image, as the way it's presented, is different. So with that in mind, it's a pretty neat trick, and using that you can create more data to train on. I wouldn't recommend flipping it up to down because rarely will you find real data where the image looks like a inverse, where the floor is facing upwards and the roof is facing downwards. So that isn't a representative of real life input data, and it wouldn't help unless you are working with a scenario where, similar to how let's say someone may provide you an image that is skewed, more so likely, instead of being upright, it's lying on its sides. So that's a common picture to be taken. And with that, you might actually now flip it in that direction to create more data, but up or downward is a rare case. And your model shouldn't suffer too much based on that, but it doesn't help you, especially if you know that you are real, what you'd consider the validation set, which is real life data, not augmented to create more data for you. If that type of data is rarely about to come in, then you have no advantage of working with that. So yes, if you are interested, you could also do the side flips. So one to the left, one to the right. And basically with that, you'd move from 25,000 to 100,000. So that would create 3 times more the amount of training data you had from flipping it left to right, then flipping it on the side, both sides. So you add that up, you have the 3 data. So still, in this case, I'm going to be working with just that single flip. And since right now, every single iteration through the for loop will be appending 2 results to the training image data, which is just the zeros and ones for the images. It's also a good idea to have the labels appended twice, so once and twice for whatever category you're speaking in, whether it's a cat or a dog. So the next step is, with that, you have your training images data. So what I'll do here is pretty similar to what I did prior, is create an NumPy array with the training images, and then a NumPy array with the images labels. Append that to basically reassign it to the same label that you had. And for the images data, do a reshape with a -1, the width and the height, then a 1. That's all. Then do a pickle dump for the training images, do a pickle dump for the test images, and finally a training images labels. And here I'm using the proper name so I can identify which type of data that I'm using. In this case, it's a grayscale training images labels, grayscale test images data, and the grayscale training images data. So the final extension here, .pck, isn't really necessary, but it's one of the things that you would add to a file to help you identify what it is. So without it, you may just think, you may be confused as to what the internal data of the file is, but once you see pck, it just helps you know what the data is. So even without adding this extension, I could have been able to read the data. But yeah, it's an advisable thing to do just to help you out later on. So also here you have WB, which is write bytes, and with that you now write bytes to the pickle file, which is now this. And so with that you now write data to the 3 files, and with that you can confidently say that you completed the whole process. So now you have the model name, which is Grayscale Model Epoch 100 Convolution 5x5. So that describes the name of the description of the model of how it's going to look. And yes, so now since the training data is completed, I can now move on to the next step of creating the NumPy array list, saving the pickle file for the first file, saving the pickle file for the second file, the third one, creating the model name, and now moving on to training the model. So this model has a 5x5 sliding window, which is bigger than the prior one, which started with a 3x3. The advantage of this one is a larger window allows it to see more data. It's also starting with a 64 cells at the top, so more info going on to the lower cells. Same layout, still moving down on the ReLU. Max pooling of 2x2, then a convolution 2D with 32 layers, 3x3 window, a ReLU, and then a max pooling of 2x2, decreasing again with a convolution 2D of 16, the 3x3, an activation of ReLU, and then a max pooling of 2x2. I then finish by flattening it, running it through a dense layer with 50 cells, an activation of ReLU, a dropout of 0.5, a dense layer of 1. So now this one is now the one that's going to determine whether it's on and off. Now going down to a sigmoid function, which is the S function that I showed prior. And the same layout here with a binary cross entropy, optimize of Adam, matrix of accuracy. So this is now telling what I want to see below here. That is now the accuracy changing over time. So as you can tell here, it's slowly picking up. If you pay attention to this, you'll notice that the percentage may wobble over time, but more or less it moves upwards, which is a good thing, which shows that it's learning properly. Additionally, you can see of the 40,000 images, how many it's actually gone through. So it had also a 20% split. So from the 40,000, there's a 20,000 used for validation. And as I mentioned prior here, the epochs means it's going to iterate over the same data an X number of times. In this case, I've set it to 100, which is almost an overkill compared to the prior case. But I actually now want to mention a couple of things that will actually mean that a high number like this won't mean I'll actually need to wait for me to reach 100. So what I have here is, starting from the top, is the TensorBoard, which is the same as what we had prior. But since the model name is different, it's going to appear here on TensorBoard as a different model training. So right now we have now our grayscale here, and since it's not actually finished a single epoch, I'm not able to see its line here. But once the first one has been finished, you should be able to tell its training model and how it's moving over time. So back to this, you have the early stop. So what an early stopping means is if the validation loss, which is what we've provided here as the monitor, which is this loss, if it goes through 5, which is where what I'm providing here as patience of 5, if it goes through 5 epochs without decreasing, so similar to what you have here. So this one deals with the loss, and I'll remove the smoothing so that I can emphasize what we have here. So let's take, for example, the lowest point we have here, which would be this. If it moves upwards, that counts as a loss this epoch didn't actually decrease the loss. Moving on to the next one, this one failed to decrease the loss. The third one and the fourth one. So if a fifth one happens without going lower than this, the sixth one will terminate. Then using that, and what I've actually added here, which is a checkpoint, which now will look for the model that had the lowest validation loss by saying save best only, which I provide as true. So from this, it's only going to save the best model, and using that and providing it as one of the features of the callback, which prior we only had the tensor board. Now we have the early stop to stop it when the validation loss has decreased too much. And finally, the checkpoint to provide the most efficient model with the lowest loss. So adding all of this up, you have your model with the best training information. So adding all of this up, we'll go through the 100 epochs, and it will terminate when it's gone through 5 epochs without any change in the loss, and the checkpoint basically will give it the best model. Now additionally, the ETA, as you can tell, which is how long it's going to take, is a smaller amount. The reason for this is I'm using a 64 by 64 image, and that means that every single image takes a short amount of time to process. So the larger the image, the longer it takes. The smaller the image, the shorter it takes. In this case, having a smaller image is an advantage on my end, because even with an expectation of an higher epoch, this should actually more or less take a short amount of time than what it took prior. Additionally, allowing it to go through the whole process until it gets to the minimal low point possible is also an advantage. One thing additionally that you could think of is increasing the patience. So maybe you may actually be interested in going 10 epochs without any change. That's not something to worry over, because even if it still goes over 10 epochs, you'll still get the lowest, the model with the lowest point. So that works out to your advantage. Yes, so adding these all together, you have a fully functional training model. So finally, what I can say is you have model.save with the models, the model name, and then a .h file, which is just how you provide a model name for Kerasmus training models. And with that, you'll have trained your model, and from TensorBoard, we'll be able to review how well each model performs over time. And so since this training actually doesn't take too long, we should be able to review this epoch and be able to tell if the first instance was actually better than the prior instance that we had in the last case. So with that, I'll be able to tell from TensorBoard if the data as it changes over time, if it's actually performing better off or worse off than what we had from just the bare-bone edges case. And my prediction is actually the grayscale will perform better off, because not only is a grayscale a more feature-rich image, and while not only is it a feature-rich image, it's also, in this case, providing it more data. So each epoch has 40,000 image to train on, where prior it was 20,000 image. So more data and more feature-rich data. Adding those two together gives you a better result. Though on the other hand, you have a model that has been reshaped in a different way. Primarily the reason for this is I actually wanted to make sure that the model, based on how I've seen other data scientists design this, find a model that I can actually perform well enough. So if my hunch works out okay, this combination of events should actually make the model perform better off than what you had prior. But as I noted before, if you note at any point that the graph is not performing as you expected, to give you a real world example, so let's say you have run this first example and you have your graph, and in this case we'll assume that this graph would be this one for the grayscale. So after some consideration, you've decided that you want to increase the value for the first convolution to D from 64 to 128. Maybe change this one to 5 to 5, and maybe this one to 32, and still keeping this one to 3 to 3. Maybe increase the first dense layer to 100, and maybe even patience to 10. So that last one will just mean it will train longer. The others are more likely to affect this more. So maybe when you increase the image sizes to, let's say, 80 by 80, or whichever the case, just make sure that you include each step-by-step process here. And whichever the case, the number of changes that you made, you'll rerun your model, and additionally I'd recommend you remember to change the model name so that now it doesn't overwrite this, but it actually now comes as a new line, a new item here. So with that, you'll be able to see how your model performs over time. So if you see your model is coming up lower than what you had prior, and it's continuously not performing compared to this. So if you were to look, pay attention to my mouse as a demonstration of how the graph would be. If you had your graph moving like this, basically not being able to perform as well as what you had prior. And since you are comparing two things, in one case it's the accuracy moving higher, and also is the loss moving lower. Though these two graphs tend to have a one-on-one correlation, if you find that your loss is moving lower while this one is not moving higher, it is something I've never seen done before, but it's more likely you'll have your loss staying higher. But if you're to notice that the loss is staying lower, then that's something to consider as a big plus. Maybe later on the accuracy will pick up as it generalizes, but these two are basically a description of the same function. So they should have a one-on-one correlation. Yes, so based on that, if you have to look at this and see that it's performing poorly, you can terminate the model while training the model, learn from the last few changes that you've made, consider the next level of changes that you want to make, change the parameters, change the model name, restart the training, review the results as it happens live. So that's how majority of data scientists work when they're using this platform of Keras, TensorFlow, and TensorBoard. And TensorBoard has been considered to be a revolutionary tool for people who are actually using TensorFlow to do machine learning. So now that this is finished, we are now moving on to the second epoch. And if I do a refresh, should be able to now see the data points for this. So you have your grayscale model here. Okay, so this is the point. interesting enough, I can't. So usually what I know is that's supposed to be possible is being able to see both graphs at the same time. But in this case, I'm only able to see the edges line only. Okay, so I'm not sure if the reason is this hasn't yet saved the data, because it's supposed to go into the logs folder, and the logs folder should basically log this. Okay, so we have the grayscale model, and it has its data. You have the edges model, and it has its data. So interestingly enough, on the graph, there isn't the distribution information. So it's been a while since I've used TensorBoard. So I am curious to wonder why it would not show both graphs, because this is a feature that was a selling point for this. So another thing that it's supposed to do is reload the data every 30 seconds. So that's one thing that here it's supposed to be able to do, and there it is. So it's now trying to reload the data. And one thing that it's supposed to do is if I hover at any point, it's supposed to show me the data of that epoch compared to all available epochs. So I'm just going to let this run till it finishes and see if TensorBoard will have at any point show this. My guess it's probably just a minor delay that's happening because of it's a minor delay happening while this is now trying to preload the information. So if that's the case, then waiting for the second epoch should fix it. If not, I'll do some research, find out the solution, and discuss how to fix it. So the good news is actually once the second point was finished, the second epoch, I was now able to see the points. So now I can see the first point and all the points that followed. So it seems in this case there wasn't any issue with the graphing logic. And so the only thing that I need to do is give it time to basically go through the whole process and continuously update the graph. So an interesting thing is right now the grayscale is proving to be performing less efficiently than the borders, but we've just only gone through the first and the second epoch, now running through the third. So relatively speaking, it's too early to tell because these graphs do tend to spike up very quickly. So if I just go to about 0.6 here, and with that you have your two graphs And so basically these points do tend to be more erratic over time. And so the first few points may come up as under, then it quickly shoots to the top. So it's too early in a sense to tell whether this is working out or not, or basically this is going to be a model that's going to perform poorly compared to the prior one. So we just give it time and see how it performs. But yes, I'd say it's still too early to tell whether the couple of changes that I've done perform better or not. But still, regardless, I'll let it run to its eventual finish so that using that, you'll be able to see how an early stopping system works. And I expect it will perform eventually better than a model without early stopping, especially one that was just running through 10 epochs. So for now, we'll just leave that to continue until it's reached the end. Then we can review how it looks. Okay, so the training has now completed, and it went up to 29 epochs before finally settling at an accuracy of 82% with a validation loss of 0.5. So if I review how it looks on the graph, you can tell that it started out slow, then it started to converge quicker and quicker, and at well, this is the 8th epoch. That's when it was almost converging, and in the 9th epoch it decreased a little bit, 10th, 11th, then by the 11th it had already catched up, then it continuously went higher and higher till it eventually stopped. So if you look at the epoch loss, this one at 7th, it was still higher than the prior one for the edges, but by the 8th one, it was already giving you a lower validation loss, which if you now compare here with the 8th, the inverse is the case. So in a sense, the validation loss was lower while it performed better in this case, it went down quicker than the accuracy. So the validation loss continuously decreased, and I believe this is the point where it went to the lowest with an accuracy of loss value of 0.48. And here, since it's going to look for the highest accuracy, which I still think it's just move the smoothing. So yeah, so the accuracy will still be around just there, 77%. And here we are getting an accuracy of 82%. So this must mean, okay, this has to be the one for the validation set, not for the training set. So this is the training set accuracy, while there is the validation set accuracy, which you can see here as 77% versus the accuracy during training. So here you get 77.3, and now you also get, as you can, if you look at the bar that's now appearing, this pop-up that's appearing at the bottom, you'll see that the grayscale model epoch has a smooth value of 0.7735, which is now the same as this. So in a sense, what this means is the training accuracy is only relevant as a consideration of how close it is to the validation accuracy. If they deviate largely, then there's an issue of it generalizing. But if they are close to each other, in this case, you're seeing, let's say, roughly about 8 or so about 5% deviation between the two. And I'd say if it's even up to 10%, it's acceptable. Depending on the complexity of your data set, you could uh, be satisfied with a validation and training accuracy difference of up to 10%. Especially for a good example for this might be analyzing real-time data for, let's say, for example, if you are observing, let's say, for example, traffic, and you are trying to predict when the traffic would occur, and what you're getting as an input is how many cars are on the road and then where the traffic occurs. So just as an pure example, let's say that you got your training accuracy to about 80%, but your validation accuracy was about 70%. That's a good enough differentiation. Even to a point, even 65 or even 60 may be still better, though it's closely now moving towards almost a flip effect. But if in this case it's actually predicting a certain point where the traffic would be. So let's say every single junction that may or may not have traffic comes as an on and off case, and you have a 60% correct prediction. That's pretty good. So in this case, you're also going to consider where it's giving false positive and false negatives, and that's a bit more in depth when it comes to machine learning. But just to finish off with this, every single validation accuracy here is basically what will be considered as near true accuracy of what you may actually get if now you used an actual validation set, which in our case here would be using now this test folder and then classifying all these images here, whether it's a cat or a dog. So with that finally done, the only thing that you need to finish up is saving your model, and now you're complete. So in the next video, we'll do the final episode where I'll show you how to do the same thing with the colored images. And with that, you'll know how to do cat versus dog classification using different sets of images inputs and also using batches or chunks.